All right, so why do we need the scatter plot and the correlation coefficient? Well, that's going to bring us to this lesson here, which is about the least squares regression line, or LSRL for short. And so again, this stands for the least squares regression line, which is the line of best fit that minimizes the sum of the squared errors. So essentially what this line is doing, it's taking all the differences here, all the errors, it's squaring them, and it's minimizing them. Meaning that this line is going to try and capture as many of your data points as possible based on the information given to it. And its line usually models y hat equals a plus bx. Now, it looks kind of familiar to y equals mx plus b, but in nature, most times it makes sense to occur at the 0th point and then start your slope. So we're going to switch that around here. So a is going to represent our y-intercept, or our starting point. B is still going to represent our slope. X is our explanatory variable, and y hat, that hat on the y there, stands for the predicted response variable. So if it's got a y, that's the actual response, but if it's got a y hat, that's the predicted response based on the model. Now, what's important about this line is that correlation, right, is the product of the z-scores 1 over n minus 1 times the sum of the products there. So what's important is that this line is going to pass through the average of the explanatory variables and the average of the response variables. And then from there, it's going to try and minimize the sum of the errors squared. So this line has a lot going on to it, and then based on this line, R is calculated, which is the correlation coefficient. And then also about this line, I should be able to tell direction, form, and strength, and any other unusual departures from that linear pattern there. So there are some important things we need to interpret when we use our LSRL. The slope and the y-intercept. And these shouldn't be too new of concepts, right? But if they are, all bueno. We have some specific interpretations that we use here. So for the slope, we're going to interpret as for each additional explanatory variable, we predict the response variable to increase or decrease by this many units. The y-intercept will be, if the explanatory variable is 0 units, we predict the response variable to be y-intercept units. Again, all of these are just sentence stems for you. You'll replace them with the context of the problem. And lastly, a prediction. For an explanatory value of x, we predict a response variable of y hat units. So again, a bunch of hoopla doesn't really make too much sense. So let's actually put an example to it and see how we would use these interpretations. So the average lifespan of American women has been tracked, and the model for the data is y hat equals 73 plus 0.2x, where x equals 0 corresponds to the year 1960, and y hat is the predicted lifespan in years. Explain the meaning of the slope, the y-intercept in context, and then predict the lifespan of an American woman born in the year 1983. All right, so we have all our various components there. So let's go ahead and try this out. So here I can see that y hat is a plus bx. So a is my y-intercept, that's 73, but my first point here is the slope, which is going to be that rate of change, that 0.2. Not 0.2x, but the 0.2. Okay, so let's go here. Let's go part A. So for each additional year from 1960, because x is measured in the years, so for each additional year from 1960, we predict, and let's look at our slope here. Our slope is positive, so our correlation coefficient is going to be positive. So for each additional year from 1960, we predict an increase in lifespan by about 0.2 years. And for part B here, okay, so think about it. So for an American woman, all right, there's your lingo for the day. For an American woman born in the year 1960. Now, this is a little wonky here, so remember, the y-intercept is when explanatory variable equals 0, but here, since x is the number of years since 1960, if x equals 0, then the year is 1960. For an American woman born in the year 1960, we predict her lifespan to be about 73 years. So the slope is the rate of change. So for each additional year, how much should lifespan be changing? And then the y-intercept is, if there were no years happening, there was no change, what would be that predicted amount? And so we can see there from the two elements from our LSRL, we're able to make some predictions and interpret our data here. Now the fun part is, let's use our model to predict a woman born in the year 1983. Now, I don't really know all of the data here, right? I don't know if this is from 1960 to 1990, 1960 to 1980, but we're going to assume that it's safe to assume we're not over-predicting or out-predicting because we were asked to find it. Now, in later lessons, it'll give us more context so we can actually determine if that prediction would make sense. So here, for part C, I need to find X, which would be the number of years since 1960. Well, I'll just take the difference between 1983 and 1960, and that's going to give me 23 years. So next up, I'm going to use my model here, and I'm going to substitute in 23 years. So I've got the base of 73 years plus 0.2 for each additional year, and that's going to give me roughly about 77.6 years. And so let's interpret this result here, because the model, the prediction, great, we can plug things in, but the power of statistics is interpreting what that story means. So for a woman born in 1983, we predict her lifespan to be about 77.6 years. So nothing too crazy, right? She's not living to be infinity. She's just gained some insight there. She's gained additional years. So that seems like a relatively accurate prediction there. So you can see just from various components, we can ask you to interpret slope, the intercept, or to use the model to make a prediction. And of course, if you get stuck, just go ahead and use your sentence stems here to help you out. And that's going to bring us now to our examples. So I have one example about fish and another example here about grades. So go ahead and, oh, I didn't even realize CDE should have been ABC. You know what? It's fine. So go ahead and pause the video here, take a look at these examples, try them out, use your sentence stems as needed, and we'll come back together to review the answers. So go ahead and pause the video and try your best. Alright, so hopefully you took a few moments there to try out the sentence stems and the practice. So let's go ahead and review here. Hopefully you read over the context here, so I'm not going to bother with that. But for each additional increase in the pollution index, we predict fish deaths to increase by 9.61 deaths. So from whether my pollution index is going 3 to 4 or 8 to 9, for each additional increase in that index, it's going to increase the number of deaths by 9.61. Now, assuming there's no change, or for a pollution index of 0, we predict the number of fish deaths to be about 111.96 deaths. And then lastly, for a pollution index of 5, we predict the number of fish deaths to be about 160.01 deaths. And then here's my work for the problem shown here. Just substituting into that model. And I apologize, I feel like I did all positive examples. There are negative examples, so you would just swap out this increase to decrease. So hopefully you'll forgive me. And I did figure out that this CDE is because here's parts A and B. I just didn't list it. Whoops. So here, a mathematics teacher wanted to see the correlation between test scores and homework. The actual homework grade X and test grade Y are plotted below in the scatter plot and yield the following linear regression equation. Y hat equals negative 20.02 plus 1.2x. And so predicted test grade, and then here's our homework grade. We are told, right, so in the scatter plot I can see it looks positive, linear, and strong, but then I'm also told the actual value of the correlation coefficient. So here I can say that there appears to be a strong and positive linear relationship between homework scores and test scores, and I can verify that using the scatter plot. Next up, I'll use my model here to predict a test score. So if I use my model and I substitute in a homework score of 70 points, I'll predict a test score of about 63.98 points using our LSRL here. Now our slope of the model, this is the rate of change, this is attached to our explanatory variable. So for each additional homework point, I'm going to predict an increase in test scores by about 1.2 points. And on the other hand, if I interpret the intercept here, if I get a 0 on my homework, or for a homework score of 0 points, we predict a test score of negative 20.02 points. And you got to stop and ask yourself, wait, doing nothing and still getting a negative score doesn't really make sense in the context of the problem. So if you want, you can add an additional context sentence just saying something along the lines of, this is not possible as test scores must be between 0 and 100. So you can always add that in when talking about the intercept. I didn't do it here because it's not standard practice. I'm just predicting based on what this model tells me. But we can see that that is a bit of an extrapolation, or it's kind of outside of our realm here, so it wouldn't be necessarily the most accurate prediction. And then lastly, we switch it up on you. So instead of asking for a prediction, I was asking for the explanatory variable that will help you obtain this prediction. So what homework score is needed to obtain a test score of 85? So here's my LSRL, y hat equals a plus bx. I want to solve for x, so I'll subtract a from both sides, divide by b. I love the literal equations approach, and then going back and solving in Fourier variable. I learned this through my first 2 years of engineering school. To each their own if you just want to plug and chug, but for my future engineers, get into the practice of solving algebraically first and then subbing in. So I'm going to go here and substitute in my quantities, and I get that getting an 87.52 on my homework should lead me to get about an 85 on my test score. So that's going to conclude our LSRL study there. So these are prediction points. These are the y hats. And the next lesson, we're going to talk about the residuals, which is the differences between actual and predicted values. So up until this point now, we can describe scatter plots, we can interpret the correlation coefficient, we can interpret slope, we can interpret the intercept, and we can make predictions using our model. So stay tuned as we learn more about residuals and some other components of linear regression.